Hi, my name is Rasmus Pagh, and this is the dry run of my inaugural lecture at the University of Copenhagen this afternoon. And I thought I might as well record it in case some people might be interested in watching it later. So the talk is titled Taming Randomness in Computing. And one benefit of postponing this for so long, it's been more than 2 years since I started as a professor at University of Copenhagen, is that there are now nice new tools that you can get help from when making such presentations. For example, this illustration of a lion tamer trying to tame some random dice. And kind of emboldened by making such a nice figure using the DALI generator, I thought, well, why not continue and ask, ChatGPT for some ideas about what this talk could contain. And it actually, came up with a very nice syllabus for a whole course. And I thought, well, okay, that's maybe too much. So let's try to ask for something more specific, something that would actually might conceivably fit into a 30-minute lecture and would actually be about something that I worked on. And, it actually did a pretty decent job, right? It suggested several topics that I actually worked on and so forth. But it kind of looked a little bit on the surface and a little bit kind of a big picture survey, and I thought it would be a bit dry, right? So, but maybe we could, lighten it up a bit. How about, maybe starting up with a nice joke? Okay, so here's a joke about randomness suggested by ChatGPT. So why did the random number generator cross the road? To get to the other side of the probability distribution. And I don't know about you, but I basically thought that wasn't funny. And ChatGPT, was slightly annoyed, but suggested that we just move on to the lecture topics. So let's actually do that. Okay. So instead of giving you this grand overview, I'm going to give you more like a small taste, a small corner of stuff I've worked on, but I think gives you the taste of the kind of research I'm fond of. Okay. And we're going to start with an appetizer, which is actually not my work, but work by other people that I've built on. And we are going to be looking at a toy problem. So why do we look at toy problems? Well, when, there are real problems to solve. And I guess the idea is that toy problems can often kind of capture the essence of a particular problem. And, whatever way you find of solving the toy problem can actually help you solve, real problems of importance. Okay. So what is the toy problem? So we're giving a collection of objects. Some appear several times, and we simply want to determine how many there is of each kind. And, this is probably the kind of task you were given in elementary school in math, right? To make these kind of histograms with different categories. And this is also kind of computationally, this is easy, right? So in the first semester, you learn efficient algorithms for sorting and hashing and so on that will allow you to build these quickly, even if there are lots of objects. So let's try to make it a bit more challenging, right? So now we had the lights out, basically. So we still have a collection of n objects, but we cannot really see them. So the task is still the same. We want to determine how many there is of each kind. And what we can do is to look at each object once. Okay, so one at a time. So we can look at the horse and then the plane and then the bear and so on, right? But whenever we move on, we cannot really remember everything that we have seen, right? So we can store only a very limited amount of information. And specifically, I'm assuming that we can store only one integer. And also this integer cannot be too large, right? So let's say that we have n objects and the integer can be size at most n, right? So let's call this integer x, right? And maybe, you wonder, why am I making these weird restrictions? But actually they turn out to be relevant in a bunch of situations where you, for various reasons, cannot access the whole data at once, right? So maybe the data doesn't exist yet. So it's kind of being generated object by object. Maybe it's kind of distributed for, maybe it's stored in somewhere where it's, expensive or difficult to get to. So again, this toy problem kind of abstracts a lot of settings. So what can we do with a single integer and just going over data? So one thing that is kind of immediate is that if we are interested in counting a specific object, so for example, suppose we are interested in figuring out how many planes there are, then we are in good shape. So we simply keep a counter. When we see a plane, we increase the counter, and so on and so forth. Every time we see a plane, increase by 1. Every time we see something else, don't do anything to the counter. Right? And we just go over everything once. And at the end of, when we've seen everything, we know that there are 4 planes. So let's call that C of planes. So that's the number 4. Right? But of course, this requires that we determine in advance what we're looking for. Right? So here's a different way of viewing what we are doing. So we basically assign a weight of +1 to a plane. So every time we see a plane, we want to +1 to the counter. And to everything else, we assign a weight of 0, right? We don't want to add anything to the counter. Equivalently, we want to add 0. And again, these weights, really require that we know what we're looking for. So we cannot really, if we don't know what we're looking for, we cannot really get to these weights. But what we can do cheaply and efficiently is to get random weights. Okay. So for every object, we assign a weight, and I'm going to focus on the case where the weight is either +1 or -1. Okay. And how do we get these? Well, I won't explain it in detail, but basically there's a cheap way of computing a particular weight for an item. So each time we see a bear, we can make a small computation, and that tells us that the weight is +1. Each time we see a horse, we can make a small computation, and that tells us that the weight is -1. Okay. Now we can kind of compute weighted sums, right? So we see the horse, its weight is -1, so we subtract 1 from the count. We see a plane, its weight is -1, so we subtract 1. We see a bear, its weight is +1, so we add 1, and so on and so forth. So we go over all the objects, add and subtract, and in the end, we end up with kind of a weighted sum. Okay, and in this case, it's actually equal to 0. And if you think about it, it's not so surprising that it's 0 or close to 0, right? Because kind of half the time we add, half the time we subtract, right? So these things will tend to cancel out. So this seems at first glance like a really, useless thing to do, right? We do a lot of work and we end up with a counter which is 0 or close to 0. Okay, so what can we do? What is the motivation for counting with these random weights? And in particular, on average, a particular object contributes 0 to the counter, right? So no, the plane might contribute -4 or 4 depending on the weight, but in expectation or on average, it just contributes 0. But here's the trick. Okay, so if we multiply by the weight, if we multiply x by the weight of a particular item, then something happens. Then actually, no matter if the weight is +1 or -1, we get a positive contribution in expectation. So if we look at the weight of the plane multiplied by x, then suddenly the expectation is not 0, but it's actually the count of the number of planes. Okay. So that seems a bit magical. So this was kind of made explicit first by Alon, Gibbons, Matthias, and Segedi back in 1999. And you can kind of do this for all the items, right? So you just have a single number x, but for every item, if you kind of multiply x with kind of the weight computed by this function, you get something that is the count of this item in expectation. So somehow you have, in this single number, you have some information about all the counts of all the items. Okay. But this is not really infinite compression, right? It seems like we have compressed arbitrary amount of information into a single number, but the thing is that the variance could be high. Okay, so it might be right in expectation, but there could be a high variance, right? So somehow, if we want to make use of this, we have to tame the variance. So let me tell you about a couple of techniques for taming variance. Okay, so the first idea is to repeat, right? So if you're unsure about something, you do several trials, right, independently, and then you kind of look at them all. Maybe you compute the average, maybe you compute the median, and it's easy to see that both of these things are going to give you something that is still has the right expectation, but the variance is also going to be increased. Much smaller, right? So it's going to decrease by a factor around k. So that's kind of the first technique. The bad thing about this is that it might require a lot of repetitions. Right? There's another idea one can use, which is to split into subproblems. We have all these items, rather than dealing with all of them at once, why don't we kind of split them into some manageable subproblems? So this is a very common technique in computer science. So let's say that we split them into B parts, and we want to do this kind of consistently. So every time we see a plane, it has to go into the same plane. So we want it to look something like this, right? So now the planes are together with the horses, the cars are together with the magnifying glass, and so on. And each of these problems seem more manageable, right? So it's and again, we don't really pay much to do the splitting because we can store one of these hash functions that basically assigns kind of a random part to each item. Okay, and now we can kind of do the estimation for each part separately, and you can also show that this actually reduces the variance. So now, around 20 years ago, some people analyzed or thought of the idea of combining these two techniques. So this was done by Charikard, Chen, and Barrett Colton in 2002, and then 7 years later, kind of rediscovered in a different context by some people in machine learning, Weinberger, Dasgupta, Langford, Smola, and Attenberg. So now we are going to look at it slightly more abstractly. So this histogram that we want to compute, we think of it as a d-dimensional vector, and we want to map it to a lower dimensional vector that still contains the essential information about the histogram. And the idea is the same as before. So basically, each time we have a count, like 4 planes or something like this, we want to either add or subtract 4 from several places in this sketch. And where we add or subtract and whether we add or subtract, we let these random hash functions determine that. Okay, so this gives us some kind of object, and it's actually very easy to implement. So this is kind of the formula for it. It's just a few lines of code. So it's really trivial to implement, but the difficult thing, of course, is to understand what happens with all this randomness. So can we really tame it? And this turned out to be very, very useful. So both of these works have well over 1,000 citations, and they have influenced a lot of follow-up work. So either extending this or using it directly. Okay. Charikard et al. Called this count sketch. Weinberger et al. Called it feature hashing, but it's really the same thing. Okay. So what I'm going to do for the main course of the talk is to tell about some work I've been involved in that kind of extends or builds upon these papers. Okay. So on to the main course, and let me just present you with the menu. So you can see we start in 2012, my paper with Ninh Pham. And then the other 3 papers are more recent. So, and actually all highly influenced by BARC. I'm really happy to be at BARC and be able to work with all the amazing people at BARC. And these papers have appeared in machine learning conferences, and there's one that is kind of brand new and has yet to appear. Okay, so let me start from the beginning chronologically, and to explain what this paper is about, I need to explain something called bilinear pooling. And essentially, the idea is that we have this vector that somehow you can think of it as representing features or some kind of data. So we can think about it as a small collection of objects. And bilinear pooling, basically, what it does is that it goes from considering these features individually to considering all pairs of features. So if we have n features first, we end up with something like n squared pairs of features. Okay. So this gives you a much bigger, much more high dimensional vector if n is large, of course. And this somehow contains more information about the interactions of features, but it's also, of course, computationally more challenging to deal with. And maybe, there's enough redundancy in this vector that you can actually combine it with feature hashing, or this kind of compression that we talked about before, that actually maps these features down to a much more manageable vector that can be stored in small space and where we can have efficient algorithms and so on. But of course, doing this transformation is still expensive, right? So we need to do the bilinear pooling, find all pairs of things, and even though we end up with something small in the end, there's a big cost. So what Neil and I found out, and we call it tensor sketch, is that there's actually a shortcut. So there's an algorithm that goes directly from the feature vector to the feature hashing of the bilinear pooling vector. Okay. And I'm not going to tell you much about it. If you're curious, there's a nice article on Wikipedia actually explaining how it works. But essentially the idea is to use some algorithms developed by others for fast Fourier transform, and use them to kind of bypass this intermediate step of explicitly computing this bilinear pooling. And it's also, by the way, made its way to one of the mostly used machine learning libraries called scikit-learn. So you can also use it there if you want to use it in an application. So let's go on to the next paper. So time is running. So understanding count sketch. So with Kasper and Jakub, we were kind of wondering what happens with count sketch if you only have a small number of repetitions, right? So we use k-hash functions, and if we look at the kind of the analysis that people had made at that point, it kind of only showed good results if the number of hash functions was kind of large, right? So asymptotically, at least proportional to the logarithm of the dimension. But in practice, people were using it with 3 or 5 or 7 repetitions, which was much less than kind of what theory would promise would work, right? So the question was this really something that we could rely on, that it would work with small number of repetitions, or was it just that people got lucky and it worked in the particular cases that they used it on? And what we were able to show is that already when we have 3 repetitions, it actually gives a provable improvement. Okay, so these empirical observations actually generalize to the worst case. So that was a bit about understanding count sketch. So now let's move on to something completely different. Okay, so I asked DALL-E to give me a drawing of a tech executive having a nightmare. Okay, I'm not sure what he's having a nightmare about. It might be Margrethe Vestager or some other people from the EU really putting pressure on preserving people's privacy or making sure that tech is aligned with societal goals and so on. So what does big tech do about all these privacy concerns? Well, there's a lot of things going on, and one of the things that I actually think is both scientifically interesting and also a good thing is that they are actually working on implementing new types of techniques for kind of protecting private data while still being able to use data. And these techniques go under the name differential privacy. So it's been implemented by a lot of the big tech companies. Also, the United States Census use it to release data about the US population. And basically, the idea is to kind of add some noise to the results of computation such that the contributions of individuals kind of are almost undetectable, but nevertheless, you preserve the high-level result from the computational data set. And I won't be able to explain this in much detail, but just note that there is a simple way to make count sketch differentially private. So suppose that you have a count sketch maybe containing sensitive data. Maybe you're counting events like visits to a particular website or to a particular place, purchases, or, well, any kind of sensitive data. You might want to make it differentially private. And what you can do is to add certain amount of noise, for example, a Gaussian noise, to each entry of the sketch. Okay, and that gives you, even more randomness. So we already have the random hash functions, but now we also have this random noise on top, right? And the question is, is this still useful, or is it just, does it completely spoil the information? And one particular problem is that you actually have to add quite a bit of noise. It has to scale with the number of repetitions that you use, and you might want to use, a relatively large number of repetitions to have really reliable results. So what I showed together with Mikkel last year is that actually you can get differential privacy almost for free. Okay, so even though you add noise, kind of the way CountSketch is so robust in its estimation that it gives you, at least up to a certain point, almost the same output as if you hadn't added any noise. So you can see the theorem we show is at the bottom left. Maybe it's easier to relate to what is on the right, which are the kind of the probability distributions you get from estimating with private CountSketch versus standard CountSketch. So, and you can see that they are almost the same. So the final result I wanted to mention briefly is about taming CountSketch's randomness. Okay. So the very tightest guarantees, the best guarantees we have on the error of CountSketch, that assumes that we have hash functions that are really, really random and require a lot of space to store. So this is not really something that you can implement in general. So what we were able to do is to find or describe some explicit time and space efficient hash functions for CountSketch. And again, the complicated thing here is not the algorithm. So it's pretty simple, one paragraph description, few lines of code and so on. But the challenge here is actually understanding it and analyzing it. Here, even the writing down the analysis was something like 7 pages. So this is hopefully coming up quite soon in archive and maybe some conference. Okay. Now we are almost done, but of course I won't cheat you for dessert. And the dessert is basically some thoughts about some interesting kinds of challenges ahead. So I think there's still a lot we don't understand about randomized algorithms in general. Okay? And in particular, differential privacy, it's an even younger area than randomized algorithms. So it's been basically the last 10-15 years, people have started working on this, and it only kind of picked up really in the last 5 years when the tech companies started using. And there's a lot of these questions, are not just academic. They actually come up when you try to use randomized techniques in practice, right? So there are these great randomized techniques, but when you have randomness, of course, there's bound to be some kind of uncertainty left, right? So how reliable are these algorithms really, right? And in many cases, we know that we can make the algorithms super reliable at a very reasonable cost, but in general, I think it's a challenge to really boost this reliability and still make these algorithms attractive in practice. Another thing that has kind of not been studied too much is what do we do when the inputs actually depend on the randomness that we used in the past. Of course, we can, use fresh randomness, but in many cases, we may not want to do that, right? So I think that's a challenge in general, and we have some techniques. There's actually a connection back to differential privacy that can be used as a tool to handle this. But in general, this is largely unstudied. Another area that I think is fascinating where there's not a lot of work is, what if we want our algorithms to fit into a particular model of computation? Like, what if we want an algorithm that we can kind of plug inside the middle of an artificial neural network, for example? right? So neural networks are not, general purpose programming languages, right? So they have a certain structure, and in particular, they implement differentiable functions. Okay. So what kind of algorithms can we actually implement in a differentiable way that could potentially be plugged in and be used as a component that could speed up parts of a neural network? So I think that's quite an interesting area. And finally, and this has received a lot of media attention, I guess, also, how do we actually trust the outputs of algorithms, right? So we want our algorithms to be fair, transparent, we want to be able to verify that they do what they are supposed to do. So Jakob will talk much more about this in a little bit. And I think there's a huge challenge here, and it's definitely not smaller when we're talking about randomized algorithms that don't do the same thing every time. So I want to finish by thanking a lot of people. So first of all of those that have chosen to work with me, do research with me. So I think all of this would have been much less fun, and I'm sure that the results would be much less interesting if I hadn't had some very great collaborators. I also want to thank all of those who mentored me, some who challenged me, some who gave me advice. It's been very helpful to, receive feedback, input, wisdom from other people. I also want to thank those who trusted me to spend research funding on worthwhile things. So this was, to a large extent, what allowed me to work with a lot of great people, was that there was some funding to pay their salaries. And last but not least, I'd like to thank my family for making work not the most important thing in my life. Thank you.